Good morning, everyone. We'll get started in just a minute or two, once we have a few more people showing up. I hope Project 3 is going well for everyone. Other things to keep in mind are regrade or midterm written questions have been graded and released, so you should read over the feedback you got there. We are allowing you until, I believe, November 9th to submit regrade requests. And we won't start addressing them until after the 9th. So if you already submitted one, that's why there's probably hasn't been any response yet. This is also my last lecture of the class. Next time it's going to be Dr. Marcus Darden taking over. He's going to be talking to you about minimum spanning trees, and then going on to talk about other big topics like dynamic programming and traveling salesman problem, that sort of stuff. All right, let's get started. So this is lecture 19. Today we're going to introduce the concept of a graph, and we're going to go over some basic definitions of what a graph is, some related concepts, and some simple algorithms that work on a graph. You'll probably see more complicated graph algorithms in later lectures. So on the slide we have Settlers of Catan. The relation to a graph here is that in this board game you build paths between your cities. And you can think of this as sort of a graph where the cities are nodes in the graph and the paths between them are edges. Similarly, for this other board game here, Ticket to Ride, your goal is to connect different cities with train lines between them. And the goal, well, I think there's a bunch of different goals, but yeah, one goal is to build potentially the longest path of connected cities. Similarly, another example of where you might see a graph is with airline routes, where you have flights going from different cities, connecting different cities. Those are all kind of similar instances of graphs where it's related to how do you move around the physical world. But there are also other examples, like think of social media. Every profile on, Facebook or Twitter or Instagram or whatever can be thought of as a node in a graph, and then the edges in that graph are, which profiles follow or are friends with which other profiles. Another example from the internet is web pages and the connections between web pages. So you could have a graph where, say, a website is a node, and all of the links on that website to other websites would be the edges in the graph. So there's a bunch of different areas in which graphs are useful representations of data that we have, and that allow us to do some sort of analysis on that data. So, just answering potentially very simple questions like, is there a flight from San Francisco to Boston? Or, is person A friends with person B? Something like that. So this is kind of an informal notion of a graph. But let's make it a little bit more formal before we get into details of how we might implement one. So a graph is a tuple of V and E, where V is a set of vertices, which is just another word for nodes. So you can see here it's vertices, but I've said nodes. They're interchangeable words. So a graph is a set of vertices together with a set of edges. And the edges are going to connect pairs of vertices. So every edge can be thought of as, again, a tuple, where the two items in the tuple are the start vertex and the ending vertex of that edge. So that's pretty straightforward, right? It's just a tuple of, a graph is really just a tuple of nodes and the edges that connect them. So this is probably the most general definition of a graph. So let's see some examples, right? We saw this tree, I think, from last lecture when we were doing, balanced binary search trees. So this is definitely a tree. It's a search tree. It's not balanced. Can we also consider this a graph? And the answer is yes. Trees are graphs. Now, if we add in an extra edge, say from there to there, is this a graph? Yes. It's no longer a tree, right? Because we now have this cycle, but it is a graph. And we can keep on adding more edges. It stays a graph. What if we add an edge like this, which we'll call a self loop, or an edge like this, which we'll call a parallel edge? So this still fits the formal definition of a graph, which allows parallel edges and which allows self loops. However, we're also going to define a concept of a simple graph, right, which does not allow parallel edges and does not allow self loops. So in most cases where you have a graph, you should assume it is a simple graph unless otherwise specified. And in particular for this class, when we say graph, we mean simple graph, unless we particularly say, self loops are allowed or parallel edges are allowed. So is this a simple graph? No, it's got this edge right here, which is a self loop. Is this a simple graph? Yes, there's no self loops. Is this a tree? And the answer is no, because we're missing this edge here that would be necessary to make it connected. So, but it's fine as a graph. A graph does not need to be connected. So speaking of connected, let's give some definition of graph terms that you might already have heard, but we're just going to formalize them a little bit more. So the first concept about a graph is, can you get from one node to another by following edges in the graph? And if we have a path, so we're going to define the concept of a path, which is a sequence of edges which leads from one vertex to another, with no vertex appearing twice in this path, right? So it's a path without a loop in it. This allows us to define more precisely what a connected graph is. A connected graph is any graph where a simple path exists between any pair of vertices. So, to go back to this example, there's no path from, say, 54 to 44. So it's not connected. And a cycle, we've kind of already mentioned this when we talked about trees, but we'll define it here in slightly more formal terms, which is a cycle is a simple path where the first and final nodes are the same. So it's just one big loop. Right? So if you can find some loop in your graph, you've got a cycle. Now, we're also going to elaborate on the different types of edges that we can have in a graph. So all the examples we've shown so far were undirected graphs, where there's no direction associated with each edge. But we want to introduce now the concept of a directed graph, where edges do have a direction. And so the order of the vertices means something. It means that the edge starts at node U and goes from U to V. And we can also call a directed graph a digraph for short. And we're typically going to represent it with arrows to show the direction of edges. So here we have, an undirected graph and a directed graph. It's important to note, or one thing to think about here is how does this affect our notion of path, right? So for the undirected graph and the directed graph, we can say there's a path from 1 through 2 to 5, right? However, the directed graph does not have a path from 5 to 1, although the undirected graph does have such a path. And so this kind of also affects our notions of of whether the graph is connected or not. For a directed graph, you actually have two notions of whether it's connected. Weakly connected just means that that if you took the directed graph and transformed it into an undirected graph, would it be connected? That's weakly connected. And strongly connected means that in the directed graph itself, there's a path from between any pair of vertices. So now that we've added directions to our edges, let's also add some extra information onto the edges. So we're going to allow edges to have a weight, and this will be represented by some double or integer value that is associated with each edge in the graph. So we can think of weight as the distance between two nodes in the graph, or the cost to traverse the edge, or to go back to our example about web pages, it might be how many users click the link to go from web page A to web page B. So it can be a pretty general notion of distance or cost, and it's going to depend on your application. In the case of undirected graphs with parallel edges, the different edges might have different weights. And a lot of graph algorithms will involve trying to optimize paths in relation to these weights. And so you might want to find, a shortest or least cost path through a graph to get from, node A to node B. So to get back to this airline example that I showed a couple times, now we can classify this graph a little bit further, right? We can say that we can ask, is it directed or undirected, weighted or unweighted? And we can see there's no arrows on the edges, so it's undirected, but it is weighted, right? We do have these weights here on the edges. In this case, I believe they represent the distance between the two cities. So that's basically the definition of our graph. Data structure. Now, as we start to talk about graph algorithms, we're going to start thinking about the complexity of these algorithms. And for graphs, there's actually kind of two numbers that we're going to express our complexity in terms of, right? So we're going to express it in terms of the number of edges or the number of vertices, or both. And here, what this expression means is this is the set E of vertices, and these parallel bars on each side of it mean the number of elements in the set. So this is just the number of edges. Sometimes you will see it written without the parallel bars, which is just a little bit of math hand waviness. And this is a little bit more complex than our tree algorithms. where for the tree algorithms, we could always express the complexity in terms of just the number of nodes. But here we are going to have these two different quantities that we might trade off. And for different graphs, these two quantities, the number of edges and the number of nodes, might look very different. So we could think about having a complete graph where we have all possible edges that connect any two pairs of nodes. So all nodes are, any pair of nodes is directly connected. So in that case, we're going to have a path from, or sorry, the number of edges is going to be equal to the number of nodes times all other nodes. So this is, edges have all possible starting nodes and all possible ending nodes. And then if it's a undirected graph, we'll divide that by 2 because we don't need two edges that mean the same thing. But either way, the number of edges for a complete graph is going to be proportional to the number of nodes squared. So big O of V squared. We can also talk about a dense graph, which is one where maybe it's not quite complete, but it still has enough edges that the number of edges is proportional to V squared. And then on the other side of things, we can talk about a sparse graph where the number of edges is much less than V squared, or we could also say that the number of edges is proportional to V. And we're going to end up representing the dense graph and the sparse graph differently in memory. And we'll get to that later, but we're going to represent the dense graph as an adjacency matrix, whereas we're going to represent the sparse graph as an adjacency list. And we'll see what the trade-off is between those two representations later. And just to see an example of a complete graph versus a sparse graph versus a dense graph, here we have every possible edge in the graph, so this is complete. Here we have almost all of the possible edges in the graph, we're just missing 2. And here for the sparse graph, we have roughly 1 edge per node, or exactly 1 edge per node. You could, of course, have fewer edges, right? There's nothing that says you need to have, you can have 0 edges. 0 edges is perfectly possible too, and that would also count as a sparse graph. Our earlier example of the binary search tree is this complete, sparse, or dense? So if we look at it, we can actually see that there's 1, 2, 3, 4, 5, 6, 7, 8 nodes in it, and only 7 edges. So this is actually quite sparse. This is actually the fewest number of edges that we could add and still have this be connected. All right, so let's look at how we would represent a graph in memory. So the first is the adjacency matrix, which remember we're going to use for dense graphs. And in the adjacency matrix, we're going to have all of our vertices along the columns, along the rows, and also along the columns. And then the entries in the matrix will be 0 if there is no connection, and 1 if there is a connection. So here, there's a 0 because there's no connection from SFO to SFO, right? There's no flight that takes off from San Francisco, flies in a circle, and flies back down. But there's a flight that goes from San Francisco to LA. Also, one thing to note here is that because this is an undirected graph, this matrix is equal to its transpose. In other words, the value here below the diagonal is equal to the value above the diagonal. Or you could also say that it has mirror symmetry along this diagonal line through the middle of the matrix. So we actually don't need to store in memory the whole matrix if we don't want to. So if you care about saving half of the memory for your graph, that's a thing to do. You're just going to have to be a little bit more careful with the calculation of, given some row index and some column index, how do you get the right value if we've thrown away this half of the graph? You have to maybe swap the indices or something like that. We also here are drawing the indices into this graph as strings, but really, if you want an array index, that has to be an integer. And so you're probably going to need a hash map probably from strings to integers. So you'd be able to put in the string SFO and get out, oh hey, SFO is at index 0 in the array, or in the matrix, sorry. Now, so this stores adjacency. Adjacency just means, is there a connection between airport A and airport B? We also want to store the distance in a similar fashion. So we can have a distance matrix, which stores the distance, or rather the weight that was on each edge. And so this will let us look up the distance in the same way that we would look up whether an edge exists between any two airports. So that's the adjacency matrix way to represent a graph. Now let's talk about the adjacency list. So here we no longer are going to have a matrix. So cross this out of your head. Instead, we're going to have a list or a vector per airport. So for every airport, this list is going to store all of the airports that are connected to some starting airport. So we can see, SFO, in the matrix, SFO was connected to LAX with the distance of 337. So LAX is in our adjacency list. So SFO is connected to LAX, DFW, ORD, and BOS, and those are exactly the entries that go in the adjacency list. And so we're going to have a bunch of lists, one per airport. So we've got our list for SFO, we've got our list for LAX. We would also have lists for the rest of them. So DFW, ORD, MIA, JFK, BOS. If we want to store the weights in our adjacency list representation, we can just put the weight or the distance into each of the nodes in the list. So we can have a pair of LAX and the distance to LAX. So we can just have both of those values inside each of the nodes in our list. Now, let's think about the space complexity of each of these representations. Or first, I guess, the adjacency matrix. So since this matrix has one entry per node, one row per node and one column per node, its overall size is V squared. As I mentioned before, you don't actually need the whole matrix if the graph is not directed, in which case, you only need V squared over 2, but it's still the same big O amount of space. Another thing we can do with the adjacency matrix is we can combine the adjacency matrix with the distance matrix. So for a weighted graph, so in our unweighted graph, we just have an adjacency matrix where there's zeros, meaning no edge, and 1, meaning there is an edge, or, really you'd represent that as false or true, right? You'd have a bool to save space. For a weighted graph, we can put infinity, or some sentinel value, wherever we want to say that there's no edge, and we can put the edge weight wherever there is an edge. So to see what this looks like, we could represent all the information in our undirected graph here with this distance matrix, where we just have, say that there's an infinite distance between any nodes that are not connected. And so when you're using this, if you see, to look up, if there's a connection from, say, JFK to SFO, you'd look at this cell and you'd see that it's infinity and be like, oh, that means they're not connected. But if you see some value other than infinity, you know a connection exists and you know the weight of that connection. And I see a question in the chat, what would infinity actually be? The max int value? Yes. If it depends on what you're doing, right? So if you know that all your distances are positive, you might use a negative value to mark no connection. If you know that all your distances are less than some amount, maybe int max would be a good choice. If you're using doubles to represent your distance, you can use numeric limits double infinity, which is defined in the limits header in C++. You could also have every entry in your matrix be a pair again, right? So it could be a pair of a Boolean. Is this edge, is there an edge here? Pair of that Boolean with the actual weight on that edge. If you do decide to use infinity, just know that, or this sort of header here, know that there's a difference between double infinity, which actually represents infinity, versus double max, which represents the largest finite value. So infinity works in a little bit of a special way. Adding, subtracting, and maybe even dividing with finite values doesn't change infinity. But multiplying by 0 gives you a nam. Here, so the slides actually say it gives you a 0 in Visual Studio. I was curious about this, so I checked this just before the lecture. And I think, at least in a modern version of Visual Studio, that's no longer the case. Dividing infinity by itself also gives nam. And subtracting infinity from itself. Okay, I haven't tested this in Visual Studio, but I'm pretty sure that this also just gives nam, regardless of whether it's Visual Studio or G++. Yeah, so that's different ways that you can represent infinity, or a sentinel value for your distance matrix. So now let's talk about the space complexity of our adjacency list, right? Here we have, for every vertex, we have a list of the edges that connect to that vertex. So our space complexity is going to be, V lists plus E total nodes that are going to be, E total edges that are going to be spread out between those different lists. If we assume a random distribution of edges, we're going to end up with E divided by V edges on each vertex list. So if we want to access a vertex list, that's going to be O of 1. If we want to find a particular edge on a vertex list, we'll have to traverse that E over V length list, which will cost on the order of E over V. So then if we want to access every edge using the adjacency list representation, that's going to cost on the order of V times 1 plus E over V, or we can do this multiplication and end up with on the order of V plus E to look at every edge in the graph. So for an adjacency list, in order to represent a directed versus an undirected graph, you can think of a undirected graph as being or an edge in an undirected graph as being two directed edges, one going from A to B and one going back. So the undirected adjacency list will contain each edge twice. It's going to be under, so if we have an edge that goes from A, or that connects A and B, that's going to mean that node B is in node A's adjacency list, and it's going to also mean that node A is in node B's adjacency list. And then also, I think I already mentioned this, but if you want to represent your weights in an adjacency list data structure, your list items are just going to be a tuple of the node and also the weight. And we said that it was O of 1 to access a vertex list. Here, what this means is we're probably just going to, again, have a hash map that maps from the, in this case, string name of the vertex to its list of neighbors in the graph. So now let's move on to some very simple graph algorithms. Maybe the simplest task we can do is determine whether a nonstop flight from some airport to some other airport exists. What is the worst case, best case, and average case complexity for both representations? So for the adjacency matrix, in order to determine whether a nonstop flight from X to Y exists, we look at row X, column Y. Since this is just an array lookup, this is O of 1 in the best and worst case, and also average case. What about our adjacency list representation? Well, in order to determine whether a nonstop flight from X to Y exists, we have to find the adjacency list associated with X and walk down the whole list, or potentially the whole list, looking for airport Y. So if airport Y is at the start of the list, that's our best case. That's going to be O of 1 time. But in the worst case, that airport is going to be at the end of the list, or it won't be in the list at all. So that's going to be on the order of V, because there are at most V entries in any one adjacency list. On the average case, however, the average adjacency list is of length E over V, and so that's how long it's going to take to find a connection from one airport to another. And I see a question in the chat now. In the first example, don't we need to use 2 hash maps as well? So for the adjacency matrix, you just need 1 hash map that's going to map from the airport name to the index, and you're just going to use the same index for the row and the column, right? Because we put SFO in first position both places, LAX same position both places. So because the order is the same, we only need 1 hash map for the adjacency matrix or the adjacency list. Okay, so in the chat, he's asking to find both values. Right, so you would need 2 hash map lookups in order to find the index of airport X and the index of airport Y. But both of those lookups happen in constant time, so the operation overall would still be constant time. But you're absolutely correct that it does take 2 hash map lookups. All right, so let's move on to another simple graph task, which is to answer the question, what is the closest other airport to some starting airport X? So, and what is the worst, best, and average case complexity for both representations? So for the adjacency matrix, in order to answer this question, we find the row containing our starting airport, and then we have to look along that row to find the minimum distance. And here you can see why having infinity is a little bit useful, right? We do want to just find the minimum of these values. Infinity, fortunately, will compare as larger than any of the actual values that exist. So you can just do the minimum and get the correct answer. But so for this operation, we are always going to have to walk the whole length of the row, which is of length v, even in the best case. So our best case, worst case, and average case are all going to be the same. It's always going to be O of v. Now for the adjacency list representation, in order to solve this task, we need to find our starting airport and walk the whole adjacency list to find the minimum distance airport. So in the best case, that list that we have to walk will just have one entry in it. So this is best case of 1. In the worst case, that list will have v entries in it. And in the average case, the average list length will be E over V. And so this will be on the order of E over V. So we can see that for this algorithm, the adjacency list has potential advantages, right? In that it only takes on the order of E over V operations, which for a sparse graph, this will be much less than the V time that we have for the adjacency matrix. On the other hand, if we are using if the graph is dense or complete, this will be approximately equal to V squared over V, right? Because for a dense matrix, E is proportional to V squared. So we actually won't get any speed up over the adjacency matrix in the case where our graph is dense. Now here's another simple graph task. So we want to determine if any flights are leaving some airport X. With our adjacency matrix representation, we need to look up the starting airport, and we need to walk along this row until we find an entry that is not infinity. So in the best case, we'll find that on our first attempt. In the worst case, though, it might be at the very end, and so this could take order v time. On the average case, well, the average case is a little tricky to compute exactly how far along the list you're going to need to walk. And we don't actually really need to know this. We're just going to say that the average case is somewhere between order 1 and order v, but it's more complicated. We're not going to worry about it. For our adjacency list representation, in order to answer this question, we need to look up a node and just check if the list here is non-empty. If it's non-empty, that means that there is some flight leaving, which is the question we're trying to answer. So in the best case, that's going to be O of 1. But also in the worst case, this will also be O of 1, and in the average case, O of 1. So you can see for this question, the adjacency list definitely outperforms the adjacency matrix. Whereas if we go back, 2 slides for determining whether a flight exists from 2 specified airports exists, that's where the adjacency matrix really shines with its O of 1 lookup. So now, let's say we have a cost on each edge in addition to distance. So, we have the distance the flight will go and how much that flight costs. So how can we find the best value flight, where by best value, I mean the greatest distance for the least cost that can be flown from some airport on a nonstop flight. So here we have our airport, we have our flights and their associated distances and costs. All I need to do is I need to walk this list, and for every item compute what is the ratio of distance to cost, and then simply take the maximum value of that computation. So how many miles per dollar? So that is going to be take time proportional to the length of the list, which best case is the best case. In the best case, our list length is 1. In the worst case, our list length is v, and in the average case, our list length is e over v. So those are all questions about a single edge, and these algorithms all answer questions along the lines of some property of a single edge leaving from a single airport. Now let's talk about something slightly more complicated, which is the we're still going to leave from a single airport, but now we're going to allow stops on our flight. So we're no longer going to just look at the direct flights from SFO, we're also going to look at the indirect flights. So we might want to answer a question like, what is the shortest path from SFO to JFK, right? There's no direct flight from SFO to JFK, so we'd have to compare going from SFO to ORD to JFK versus going from, let's say, SFO, LAX, DFW, MIA to JFK. I mean, visually we can see that, this is the best path, but how do you answer this question when it's not, printed out on an image in front of you and it is instead represented as an adjacency matrix or adjacency list? So for here, for this problem, we want to find the shortest path to get to any vertex from some given starting point. And we've got some options here listed out. So the first thing that you might think of, maybe based off of our tree lectures, would be to do depth first search, as we did on the trees. First off, can you even apply a depth first search tree algorithm to a graph, right? There's one important change that you need to make, which is that a graph potentially has cycles. So there might be multiple ways to visit the same node. The way that we can solve this problem is to keep track of which nodes we have already visited and only allow our search to reach nodes that have not yet been visited along some other path. So if we do this, we'll find depth first search. It will find a path between 2 nodes in the graph, but it won't necessarily find the shortest path. So, if we have some graph that looks like this, The right-hand side is the shorter path because it only has 2 edges. But depth first search, if it starts going down this path, it's going to go all the way down this path first. And so it's going to reach our target node with a distance of 3. And it's never going to reach it along this path because we will have marked this node as visited. So when we go down this path, we're actually going to stop right here. And we'll go more in depth here in a second. So our other tree algorithm that you might remember is breadth first search. And we need to make the same modification as we did for depth first search. We need to mark whether a node has already been visited or not. But if we do this, breadth first search will actually find us the shortest path from some given starting airport. And it works because the search is breadth first, we're going to visit everything that is distance 1, followed by then visiting everything at distance 2. And because we're doing it in that sort of order, we will actually find the shortest path using breadth first search. Now, both of these are not taking into consideration any edge weights that might exist. So what if we want to find the weighted shortest path, where we want the minimum total weight along the path? We're going to see something, well, we're just going to mention it in this lecture, but it will be covered in more detail later, and it's called Dijkstra's algorithm. To give you a little hint of how it works, remember, depth first search uses a stack, breadth first search uses a queue. Well, Dijkstra's algorithm uses a priority queue, and that's how it is able to handle weighted edges. But you'll see more of that in later lectures. So first, let's talk a little bit more about the difference between depth first and breadth first search. Depth first means that we're going to start from our route. We're going to visit a child, and then before visiting the other children, we're going to visit that child's child and that child's child. So we're going to end up traversing this graph in this order. So we're going to go A, B, D, H, E, I, J, and only then do we visit C and the rest of this part of the graph over here. Whereas for breadth first, we're going to visit one child and then the other child. And then we're going to go back and we're going to visit all the children at depth 2, and then all the children at depth 3. So depth first search might, it doesn't answer the question of what is the shortest path, but it does a good job of answering the question of, does some path exist between 2 nodes? And the advantage of depth first search is that it uses a bit less memory than breadth first search. So obviously you could also answer this question with breadth first search, but depth first search is a bit more of the appropriate algorithm for this case. So how do we do depth first search? Well, as I said before, we're going to use a stack, and we're also going to mark nodes as visited as we visit them. And in code, this is going to look like this. So we're going to start at some source node. We're going to mark it as visited. Then we're going to push it onto the stack. And then while the stack is not empty, we're going to pop the next candidate from the top of the stack. And for every one of its neighbors, if that neighbor has not yet been visited, we will mark it as visited and push it into the stack. And then if the neighbor is the goal neighbor, we will return here. So we're doing this sort of early success checking, right? We're not waiting for adjacent to come back out of the stack. We check when it goes in. We check if it's the goal when we put it into the stack. And that's just going to make this algorithm run faster so that we don't have the goal sitting in the stack for a while as we search the rest of the graph. And so this actually might look pretty familiar code to a lot of you from Project 1. this, at a high level, should be very similar to what your code looked like for the, Letterman. And that's because what you were doing there was kind of a sneaky depth first or breadth first search on a graph. We didn't tell you it was a graph, but you can think of it as a graph if you think of every word as a node, and then if two words are similar enough, there's a connection between them. What makes it a little bit different than a graph, though, is that we didn't have any explicit adjacency matrix or adjacency list. We had to calculate on the fly. Does an edge exist between word A and word B? So as an example of depth first search, let's say we have this graph here, and we're going to start at A. So step one is we're going to have a stack with A in the stack. We're then going to pop A out of the stack and mark it as visited. Then we're going to put the children of A into the stack, so B, C, and D. And so that's one iteration of that main while loop. So now we're going to pop D from the stack because it's at the top. It was put in most recently. We'll mark D as visited. Then we'll check the neighbors of D. And in this case, so this is the graph we're searching, right? D has this neighbor. Oh, sorry. Actually, when we pushed B, C, and D into the stack, we should have also marked them as visited, right? So now when we look at the neighbors of D, the only neighbor of D, or sorry, the two neighbors of D are C and A, but they're already visited. So you can see here, we've marked this with this dashed line to show that, we would go from D to C, except that it has already been visited. So after visiting D, we don't push anything else into the stack. So now we go through back to the top of the loop. C is now at the top of the stack, so we'll pop it and find its children. So its child is E, so we'll mark E as visited and put it into the stack. Then we will go back to the top of the loop, pop E off of the stack. E has children B and C, but they're already visited, so there's nothing else to do here. And so finally, we will pop B out of the stack. And we're done, because the stack is empty. So what is the complexity of our depth first search algorithm with an adjacency list representation? Well, the main thing we need to do in depth first search is to get the neighbors of the current node, right? So we're going to, in order to do that, we're going to need to get the adjacency list for that node. And that is going to happen once per vertex. So that's on the order of v times that we need to get an adjacency list. The other thing that we're going to need to do is we're going to need to walk through all of our adjacency lists. And so each adjacency list is going to be on average length E over V. And so walking each adjacency list is going to take on the order of E over V time. So we can multiply these two quantities, right? So there's V cases where we need to look up an adjacency list. And each of those cases is going to cost 1 plus E over V time. So overall, DFS is going to be proportional to the number of nodes plus the number of edges in the graph. On the other hand, let's say we are using depth first search on an adjacency matrix. what's the computational complexity of this? Well, we need to get each vertex, and getting a vertex takes at one time, but we're doing it v times. So the total time for that is going to be on the order of v. And then per node, we are going to need to find all of its neighbors. And in order to do that, we're going to have to walk along that entire row of the adjacency matrix. And that's going to take on the order of v steps, because our adjacency matrix is v by v, so a row has length v. Multiplying these two terms together, we're going to get that the complexity of DFS on an adjacency matrix representation is worse, right? It's on the order of v squared. Now, that definitely looks worse compared to the adjacency list, which was v plus e. But remember, if our matrix is dense, e is proportional to v squared, so this would become O of v plus v squared, which is equal to O of v squared. So for a dense matrix, you're not gaining anything with the adjacency list representation. Oh. And there's a question in the chat about why I have written O of 1 plus e over v here. What is the 1 for? And this is just to remind ourselves that, right, so if we weren't multiplying by this quantity, the 1 wouldn't really matter, right? 1 plus e over v is roughly the same as, it is still on the order of e over v. However, since we're multiplying by v, we don't want to end up forgetting that there is at least a constant amount of work that needs to be done per adjacency list, right? Because you could imagine, right? What about if we had a graph with no edges, right? Then this term here would be 0. And if we just had this term in here, we would end up multiplying v by 0, and we'd end up with O of 0 time for a graph with no edges, which is not true, right? In a graph with no edges, you'd still need to visit, you'd still need to look up every node in, you'd still need to look up each node once. And so it'd still take on the order of v time. And there's another question in chat. What sort of time complexity is this? It doesn't seem quite like average case because we don't necessarily see all the vertices. So this expression, the final result here, is worst case, but it's also best case. We're always going to have to visit all the nodes and edges when we do DFS. This here, again, is a little bit more hand-wavy. But you can think of this as being average case. But then we're taking our average case and we're multiplying it by all the different times we hit that average case. And that's how we end up with this expression. And this is a little hand-wavy here. So apologies for that. A better way to approach getting the final answer might be to think, well, we have to visit every node. So we know that it's on the order of v. And we have to traverse the entire length of every adjacency list, which gives us e. So that's how another way you could end up at this final expression, which is v plus e. All right, let's move on to breadth first search. So here, for breadth first search, we are actually going to find the shortest path from the source to the goal node. Actually, we're going to find the shortest path from the source node to all nodes in the graph. So here, the big idea is we're just going to use a queue instead of a stack. And it's going to be the same code as before, except now we have a queue. And this is only going to find the shortest unweighted path, right? It's not taking into account any weights on the edges or anything like that. So here's the code again. And again, this is basically the same as the previous, except we have a queue here instead of a stack. So we're going to take our initial node, we're going to push it into our data structure, and while our data structure is not empty, we will take from the front of the queue, for every one of its neighbors, if it's unvisited, we will mark it as visited and add it into the queue. And we will also, again, do early goal checking here so that we don't do extra work once we have already marked the goal as visited. So we're going to look at the same graph as before. So let's say we have some queue. We're going to push the start vertex, A, into our queue. Then we hit that while loop, right? And so remember, in this while loop, sorry, I should also write down what nodes have been visited. So when we push A into the queue, we also mark A as visited. So now in our while loop, remember, we pop from the queue, and we add the children into the queue. So that's B, C, and D. And we're also going to mark them as visited. Then we're going to pop off the queue, and we're going to get B. We're going to add all of its neighbors that have not yet been visited. So A and C have already been marked as visited. E has not. So E gets added into the queue and marked as visited. So next up, we pop C off of the queue. All right, so this is another loop through. C has neighbors A, D, F, E, and B. But out of all of its neighbors, only F has not yet been visited. So we'll mark F as visited and add it to the queue. Next, we'll pop D off of the queue. And at this point, D has no more neighbors. And you can see we've visited all the nodes that are just one hop away from our starting node. The only two things left in the queue are the nodes that are 2 hops away. So we'll continue our loop. We pop E off. It has no unvisited neighbors, so nothing new gets added to the queue. And then we'll pop F off, and now we visited these 2 nodes, which are at distance 2 from the starting node. So we've gone through our graph exploring stuff in order of distance. So our complexity analysis here for BFS is essentially the same as for depth first search. So for every vertex, we need to look up that vertex, which is going to take order of V. And then per each vertex, we're going to do some amount of work, which is proportional to the length of the adjacency list. But at the very least, we're going to be doing constant work. Multiplying these 2 numbers together, we get O of V plus E. Oh, and I see a question in the chat. How did we record the distance to each node? So here, there are a couple different things you can do. Probably the most common is to, when you reach a node, record where you reached it from. So for each of these nodes, we reached them from A, and then E was reached from B, F was reached from C. So let's say our goal node was F, and we want to know what was the distance from A. Well, we can see that F was reached from C, so we can go back to C, and we're going to count, right? So that's distance 1. And then at C, we can see that C was reached from A, so we're going to go back and we count 2. So that is how you would recover the shortest path and the distance from your breadth first search. So breadth first search, again, on the adjacency list is going to be on the order of B plus E, which is the same as depth first search. And if we do breadth first search on an adjacency matrix, now we're still going to need to visit every node, or look up. We're still going to need to look up every node, but now we're going to have to walk the whole length of that row. So multiplying these two terms together, we're going to get on the order of V squared, which again sounds worse, but for a dense graph, this is actually the same as the adjacency list representation. Now, the third algorithm we mentioned is Dijkstra's algorithm. And there'll be, I think, a decent chunk of a later lecture on Dijkstra's. So all I'm going to say about it for now is that this is going to discover the shortest path, where shortest means the sum of edge weights. And how we're going to do this is we're going to use a priority queue instead of a queue, where the priority of a node is just the amount of distance so far from our starting node to that node. So nodes that have shorter distances, like LAX, are going to come off of the priority queue sooner than nodes that are also like one step away, but have a longer distance. But you'll see all this in more detail later. And with that, we've actually reached the end of our graph slides. Actually, a decent chunk ahead of time. That's good. So to summarize what we've talked about today, we introduced the concept of a graph. We talked about neighbors, paths, whether a graph is connected. We talked about 2 ways to implement it, either as an adjacency matrix or as an adjacency list. And then we talked about some simple graph algorithms. So we talked about some one-hop, one-step graph algorithms, like determining if an edge exists. And then we talked about some multi-hop algorithms. So does a path exist? And you can use depth first search for that. Or what is the shortest path? And we use breadth first search for that. And that, I'm afraid, is it for today. Next time, you'll pick up with Marcus Darden, and you're going to be talking about another graph concept called a minimum spanning tree, which is useful in a whole bunch of different algorithms. So I just want to say thank you to everyone for coming to the lectures. I hope that they were enjoyable and that you learned something, and I will not be seeing you next time. So have a good one, everyone.